So, hello everyone. My name is Alistair Hart. Thank you for the opportunity to come here and talk to you today. I work for Cray in their Exascale Research Initiative program in Europe. I'm based in Edinburgh. I joined Cray, I suppose, about 3 years ago, which is really about the timescale, about when we've been thinking about how to program GPUs in a more high-level manner. And this OpenACC programming model has grown out of that. OpenACC is about 15 months old or something. It was launched at Supercomputing in 2011. So before that, I worked in Lattice QCD. I was doing physics. So the way I kind of structured this course is the way I sort of think about these things. And it's more as a sort of user, and how do I do this? How do I do that? So the way I kind of go through the material is sort of developing it almost by examples, and what do I need to know first and what do I need to know next. Now, for some people, some people prefer to kind of just get the standard, read the standard, see how you can see what all the facilities are within the language and do it that way. If you want to do that, that's fine. I mean, the standard is, as standards go, fairly short and fairly readable. So, you can download it, you can print it out, it's 30-odd pages, and you can see the whole thing from that. But my approach is more incremental. So if you've got any questions, please do let me know. Jeff just showed the timetable. As he said, this gives us a structure for the day, but we don't have to stick to that. If there's if people are particularly interested in one part or another, then we can spend more time on that. So the slides, as I go along, if you want to look at a PDF of the slides now, the slides and the tar file with the exercises are in a directory under ~A Hart and then Cray OpenACC slides. So if you want to get the material from there now, you should be able to read that directory. If not, please let me know. So at first, when you first look at this, it does look to be a lot of material. So, I'm conscious here that we probably have a mix of people. So to try and get an idea, how many people have used GPUs before? A few. And how many people have never used a GPU at all? Okay, good. And the examples that we're going to look at, generally I've got C versions and Fortran versions. It's always useful to try and get a mix. Whose first language is Fortran? And whose first language is C? Okay, so both are there. I hesitate. C++? We'll be treating the subset of C++ called C for these. So the aim of today is, by the end of today, if you followed all the material, and you would be at the point where you could port a parallel code, a large parallel code, to use OpenACC to run on the GPU. Now, for some of you, that may be far more than you hope to do right now. It's not your immediate priority. So the idea is that if the material that's in the morning will give you enough to port a simple example. And by simple example, I don't just mean hello world. It's a serial code, one that runs on one core of a CPU or one GPU and does a calculation. It's not a particularly big code, but it gives you the tools to do that. The material after lunch starts to be a bit more advanced. It's looking at how you might do more advanced tuning of your code using OpenACC, how you might port a larger code, what tools are there to help you when the code isn't just a few, 200 lines. You're talking about thousands, hundreds of thousands of lines of code. And when it's a parallel code, what extra features do you need to think about? And then finally, the last lecture is where I'm talking a little bit more about the sort of, the much more advanced features and what's coming in future releases of OpenACC. So I last came to CSCS a year ago to talk about OpenACC. OpenACC was much was very young then. Since then, a lot has changed. CSCS has moved to this new building. When I came before, it was out at Mano at the old building, which had donkeys walking around outside. We don't have donkeys here. I haven't seen any, but the setting is, it's not just warehouses. It is a prettier setting. Turdy has moved. The XK6 was. It's grown as well, and grown from being 2 cabinets to 3 cabinets, and it's gone from XK6 with Fermi GPUs to XK7 with Kepler GPUs. I think it was the first accepted Cray XK7 system, so we're very fond of Turdy. OpenACC has also grown. There's a technical report out saying what's going to come in the next version of OpenACC. That's version 2. That's going to be, in the next few months. In the last year, Cray, PGI, and CAPS have all released sort of full compilers covering all of the language. Cray and PGI had tutorials at SC12. That's always a mark of something is becoming more mainstream. OpenACC got an award. So quite a few vendors were part of this. This appeared on the Cray booth at SC12. But PGI and other people who were involved in OpenACC from the start, NVIDIA, all got this award. Each little sign is tailored to the vendor. So whilst Turdy is the first XK7, there's 2 enormous Cray systems that have got in Cray XK7s. There's the Titan cabinet, the Titan system at Oak Ridge with 200 cabinets, each with about 100 GPUs, so you've got nearly 20,000 GPUs there. The other system is the Blue Water system in Illinois. That's mainly XE6, the same as Rosa, just a pure CPU system, but it also has 30 cabinets, a sort of little side order of GPUs, but that's still a 3,000 GPU system. And there's a lot of smaller, but no less important XK7s around. So the aims of this course are to try and motivate why a directive-based approach, a high-level approach to programming GPUs is useful, to introduce you to OpenACC, give you some experience in using the directives, and I put in some hints and tips and things along the way. Mainly this is where I realized I was doing something silly, and as kind of my penitence, I tell you about all the mistakes I make, so hopefully you won't make them. It's also to introduce you to some of the tools that you can use to understand and tune the performance of your code. Simple codes you can do by eye. You just look at the code, you know what to do. But very big codes, where do you start? How do you go about doing this? So, and the idea is that you should have the knowledge, this is HPC. This isn't just running a little kernel just to see the GPU working. You want to do it, you have a parallel code. It needs to be parallel because you're thinking about big problems. And so when you think about these big problems, they're too big for a single GPU. So you're going to want to port a parallel code from CPU to be a parallel code on the GPU. And what extra knowledge do you need to get to do that? Oh, well, this... I don't know. Oh. Oh, right, fine. Yes. So that was the introduction. So before we start talking about OpenACC, I'd like to just talk a little bit about what the Cray XK7 looks like and what the GPU inside looks like. Now, I'm not a hardware person, so this isn't a detailed view of the architecture. It's more giving you some idea about what's inside and what that means when you're porting a code to run on a GPU. Now, this isn't OpenACC specific. You have to think about the same things if you're doing CUDA or OpenCL. It's what does the hardware mean in terms of your programming things. So I thought I updated this slide. I'm afraid I've put an old version of this slide in already. The Cray GPU systems were launched as the XK6. Of course, now we're at the XK7. So what does that mean? Each node of the system, so this is a picture of the blade So this is, the kind of hardware that's slotted into the big cabinets. And on that are 4 nodes. And those 4 nodes consist of CPUs. They're lined up under here, under these heat sinks. And each CPU has an associated GPU. And the 4 GPUs are there on the board under those heat sinks. They're directly onto the board. They don't have their own fans. They're not devices you plug in. They're using the cooling of the system. So the actual kind of GPU itself looks something like this. As I say, embarrassingly, this first slide is out of date. I think I must have updated the wrong version. You have one one CPU, which is an AMD Interlagos. It's got 16 cores. There is one GPU, and this was the Fermi GPU. It's now the Kepler. So these nodes are linked together by an interconnect. You don't really need to know a lot about that. It's the Cray Gemini interconnect. It's got quite low latency. It's quite fast. And the system is very integrated. Because we're working very closely with NVIDIA, there's a lot of integration of the software. So I've already mentioned these 2 large systems. Why do we care about GPUs? We care about GPUs for 2 reasons. One is that we've got them now. And they're a good way to accelerate codes that are suitable for them. But from the point of view of what do we think about in the future, people are thinking about exascale. And if you're going to go to exascale, well, when are we going to get there? It seems to be every 10 years you make a 1,000-fold leap in performance. So back in '88, we first sustained a gigaflop on an application. '98, you got a teraflop, a petaflop in 2008. So then when people say 2018 is the exascale, this is just drawing this straight line. Now, all of these machines that first did this sustained performance were Cray machines. So obviously, we like to show this, and we're very keen to continue this trend. And to get to exascale, power is the big problem. The old Jaguar system drew 6 megawatts of power to give you 1 petaflop. The US DOE, and they pay the bills, so that what they say goes, says we will have an exaflop machine, but it's got to be 1,000-fold quicker, but only 3 times the power. How are you going to reach this? Well, it's likely you're going to need a lot of floating point units, but they're not going to be big, beefy CPU cores. They're going to have to be much more cut down and designed to do parallel work. They're probably going to need to share the instruction stream, so you'll have a lot more of the sort of vectorization. On the CPU, you've got SSE and AVX and this sort of thing, where you have a bunch of them doing a vector instruction, a bunch of floating point units. And the GPU looks a lot like that. So by understanding how to program GPUs now, we're understanding how we're going to program the next generation of supercomputers. And John Levesque, one of the Cray people at Oak Ridge, who's a big user of OpenACC, he just says it's just like the old days. I mean, like all old stories, you have to be old to know it. But in the old days of vector processors, it's very similar. And the Cray compiler has been doing vectorization for a long time. And so this was a quote from one of the EPCC newsletters saying, Seymour Cray asked in the old days, he wasn't a fan of parallel computing, an MPI sort of things. He said, would you rather plow a field with 2 strong oxen or with 512 chickens? 512 processors was unimaginably large. Well, we don't have any choice. We don't get oxen anymore. The clock speed has ceased to go up. We just have chickens, and we have not just 512 chickens. You're probably thinking about having 1 million chickens and using those to plow a field. And that's sort of like how you're using a GPU. And it's just, we're going to have these. And so there's a lot of effort to understand, it's one thing to build the hardware, it's another thing to actually use it. And so Cray is involved in a lot of research activities, looking at exascale software tools. And one example of this is the Cresta project that draws together a number of tools providers, hardware partners, HPC centers, and as well as application owners to try and understand how to get performance on things like GPUs now with a view to what's going on in the exascale. why do we need a new GPU programming model? We've got CUDA. You can do CUDA with C. You can do CUDA with Fortran, with PGI compiler. You can do OpenCL. You can do Stream on AMD hardware. There's high CUDA. There's all sorts of different GPU programming languages. Why are we, are there not enough already? All of these are quite low level, and they're closely coupled to the GPU. You have to rewrite your kernels in a specialist language. The tools for CUDA and things have improved enormously, but it is harder to write than taking your CPU code in a familiar Fortran and C. You probably, to get the best performance, you have to optimize for a particular GPU architecture. We had an MSc student, on the old Tesla 10 cards, he did a lot of shared memory optimization. He had his MSc project ready to go. EPCC got a Fermi card, so he reran his examples. All of his hand optimizations made the code slower because the Fermi 20 series card just handled a lot of caching a lot better. And all his shared memory optimizations just got in the way. So even within, a GPU family from a particular vendor, you can do a lot of hand optimizations that you have to redo for a new architecture. And if you want to port to a new accelerator, you have to redo everything because it's very architecture specific. You end up with multiple versions of the code in your code base. You've got a CPU version, you've got at least one GPU version, and somebody adds some new science, some new physics, some new engineering in the application in the Fortran or the C. Somebody has to port that into CUDA and make sure it all still works and the old stuff isn't broken by that. So having a single source base is a good idea. Of course, if you want to get good, you can get good parallel performance using CUDA. And I'm not saying don't do it. I mean, this is an example comparing a CPU machine and a GPU machine and the speed you get as you run in parallel and the performance on the GPU machine. This is an old GPU. You can beat the CPU quite comfortably. But this was a physics code by the University of Edinburgh. They spent a lot of time rewriting in CUDA the entire code. They did a lot of work reordering data structures, packing halos on the GPU, using streams to overlap things that they could overlap. They did a lot of work. They got very nice results, but most applications don't have this amount of expert developer support. But you still want to get the benefits from a GPU. So directives gives you a higher level alternative. You take your original code, Fortran or C or even C++, and you base it on that. So it means that you're sticking with the original source code. So when you say to somebody, okay, implement this new solver, implement this new set of boundary conditions, they're working with the same code that's going to run on the GPU. If you have experience of a sort of threading on the CPU, if you've used OpenMP, and I will mention OpenMP in this course, but I'm not assuming you know anything about it. But if you have used it, you'll find it familiar. This idea that you put essentially comments into the code to guide the compiler to use, for OpenMP, you're guiding it to use multiple CPUs, multiple cores to share the work. With OpenACC, you're getting it to use all of the floating point units, the cores on the GPU, to share the work. The compiler handles a lot of the repetitive boilerplate code. If you've ever written CUDA, you spend a lot of time allocating space on the device, moving data around by hand. You write a lot of repetitive code. The compiler can handle that, if you're using a higher level approach. And also, you spend a lot of time with CUDA choosing numbers of threads per thread block, number of thread blocks, and so on. The compiler can make a default decision on that. And with a higher level approach, you can step in and say, no, in this case, it's actually slightly better to do this. But it's better to step in when you need to rather than have to do it everywhere. Of course, any high-level approach, there could be a performance sacrifice. And it's important to quantify this because, if it goes 10 times too slowly because you're using directives, yes, they're really nice, but they're very rubbish. And you would be better off doing CUDA to get the performance. If, however, the performance gap is 10%, 20%, you might say, well, actually, I can live with that losing 10% of my performance on the GPU because it's much easier to use my code with OpenACC. After all, if you took your CPU code and you hand-coded it in assembler, you would probably get 10 or 20% more performance out of it. But not many people do that. So lower-level approaches aren't always the best thing to do. And in some cases, the goal of Cray is that we should see a 10 to 15% performance gap at most in using OpenACC compared to CUDA. In some cases, we can actually beat the CUDA. What does that mean? Well, it means two things. One is that you could probably tune the CUDA a bit better because you do have more control of performance. But the other lesson is that, for instance, in this example, this is one of the big applications that was ported at Oak Ridge to run on their XK7. The CUDA wasn't written naively. It was written by somebody who was out to write performing CUDA kernels. And even so, the compiler beat them. So, you are fighting against a compiler team when you say, I can definitely do it faster in CUDA. So it may not be the best thing to do. Can you get good performance if you use OpenACC? Well, for many codes, yes. If you actually, CUDA can beat the CPU, can OpenACC beat the CPU? Is it worth using the GPU? Yes, they're shiny, they're fast, but if you can't actually get the performance out, are you just better running on the CPU? And so again, this is showing that an OpenACC code, node for node, is beating a CPU machine. This isn't over one core. This is comparing 64 GPUs to 64 nodes, each of which has 2 interlagos CPUs, so 32 compute cores. So I've covered most of that already. What does a GPU look like? I got 1,000 times speed up on the GPU. People have stopped making these claims so much, but you do still see them. That's not true. What it means is that you've done something different on the GPU. What should you expect? Well, if you look at a Cray XK7, if you look at the GPU, so here's the node here that I showed you before. So you've got a CPU that's sitting under this heatsink. That does about 150 gigaflops, double precision. It has some memory, which is these cards here, and the memory bandwidth is about 42 gigabytes per second from CPU memory into the CPU. You also have a GPU. Well, that's doing about double precision, say, just over a teraflop. It's got some memory. It's not got as much memory as the CPU, but it's got a much higher memory bandwidth. So if you compare flops, GPU to CPU, well, it's about a factor of 9. If you compare memory bandwidth, CPU to GPU, it's, say, a factor of 6. So how much faster than the full CPU should your GPU code go? If you're seeing something in the range of 5 to 10, you're doing very well, because that means that's what you would expect by looking at flops for a CPU-bound code or memory bandwidth for a memory bandwidth-bound code. In between, you're going to see something around there. These ratios, I'm talking here about the Cray XK7, they're very similar to other systems. GPUs, it is harder to reach the peak performance on a GPU than a CPU. Your code does need to fit the architecture to some extent. So it's harder to get the peak. When you look at the LinPack scores for a CPU machine in the top 500 list, and you look at the LinPack scores for a GPU machine, you get a higher percent of peak on the CPU. And that's just a fact. And the other big thing is that whilst we have some nice fat pipes here, we have a very thin pipe that connects the CPU to the GPU. The CPU and the GPU have a separate memory space. They're separate things. If you want to process some data on the GPU, the first thing you have to do is send it to the GPU. So it has to go across a very thin PCI link. And whenever you're looking at a full application performance, there's almost certainly going to be some data transfer going backwards and forwards across this PCI link. So even when you look at the peak performance of this, you have to factor in that data transfers are going to cost you time. And that's going to be one of the big themes of this, this course. I'm not going to talk in detail about the architecture. If you look inside the Kepler at a sort of block level, what does it look like? It's got lots of compute cores, lots of little floating point units. They're divided into groups which are called streaming multiprocessors, SMX. And these operate independently. These multiprocessors operate independently. Everyone shares global memory, but the little multiprocessors have access to their own little bit of memory, like a cache. And when you schedule work onto the GPU, well, I'll talk about that in a moment. The SMX, so if you look at, so you've got all of these cores, they're divided into groups. If you look at one of these groups in more detail, you've got some single precision cores, you've got some double precision floating point units. The ratio of these is 3 to 1. So the ratio of double precision performance to single precision performance is going to be 3 to 1. Within there, all of these cores, they don't operate independently like the cores of a CPU. They all have to do the same thing at the same time. They operate, well, not all of them, but they operate in blocks with a shared instruction stream. So it's a lockstep. It's what they call SIMTs, a single instruction, multiple thread. So it's, if you've used vector processors in the past, it's like a vector processor. When you write your code for the GPU and it gets translated into the equivalent of assembly language for GPUs, it's all written in terms of vector instructions. It's all written in terms of these 32 cores are going to do the same thing at the same time, but on separate pieces of data. So you always have to think in this vector way. Now there's a memory hierarchy. Each core has its own private registers, because they're operating on a different part of the array, so they must have registers to hold where they're working. There's not, the register file size is not large. They also have access to a shared memory, which is quite fast. That's shared between the cores. So the cores here can all use this shared memory to exchange information. All of the cores, all of the cores in all of these blocks have access to the global memory. This is about 6 gigabytes, so it's quite big. Not as big as 32 gigabytes for the CPU, but it's relatively slow to access that. So that's what the hardware looks like. How do programs actually execute? Well, when you write your kernel, the CPU launches the kernel to the GPU to execute. If you're using CUDA, what do? The parallel work, I've got this whole array to process. So you split it up and you say that I will divide the work of processing every element in the array between a lot of lightweight threads. These threads are divided into logical sets, which are known as thread blocks. So this is just, they're in blocks. The reason that they're in these blocks is because when you send this to the GPU, each of these thread blocks, each of these groups of threads, is given to one of those 14 blocks that I showed before. So the threads in a thread block, so this subset that are executing on this particular multiprocessor, they have shared memory, and you can synchronize the threads within that. So once they've finished their work, you can say, and make sure everybody's done their little bit of updating the array before we do the next task. So that's, like the synchronization that you'd use if you were doing parallel programming on the CPU. The difference is that that's just the threads inside a thread block. But actually, you've got lots of thread blocks. These thread blocks are being scheduled on different ones of these multiprocessors at different times. They're being swapped in and out. The runtime is saying, oh, you're waiting for a memory access. Meanwhile, I'll swap another thread block in, and it'll do some compute. So it's hiding memory latency and these sorts of things by swapping these in and out. What this means is that you've got no control over how the different thread blocks execute. You can't globally synchronize because you just don't know. It might have completely finished this little chunk of threads before it even starts those over there. You've got no way of controlling this. So you can't do a global barrier and say, make sure you've finished all of this work, and then you're going to do this. You have to go back to the CPU to do the synchronization, because that's the only way to be sure that it's finished swapping all of these thread blocks in and out. The kernels launch asynchronously normally. When you say, do this work on the GPU, you just say, do this work on the GPU, and then control comes straight back to the CPU. So if you want to do something else, you can. You have to later say, make sure, you have to later test or barrier to say, has this work finished, or wait here until the work on the GPU has finished. So you're in control of this thing, which can be a very powerful thing. It can also lead to problems. And of course, the CPU is in charge of all the data. So when you send data to the GPU to process, you have to do that from the CPU. And when you ask that you make sure the GPU has finished processing it, the host then brings the data back if you want to do something on the CPU, like print out some values or write it to disk or something like this. So these separate memory spaces are a thing. Now, I said before that this multiprocessor is like a vector processor. When you say, oh, a thread block of 256 threads is going to execute on this SM, they don't all execute at the same time in the same way. The threads are actually grouped into sets of 32. Why? Because there's 32 cores sharing an instruction stream. So these are vector instructions. So your code is implemented as vector instructions, and each vector is then executed by a group of 32 cores together. So these threads within the thread block, so these 256 threads are really not 256 threads. They're 8 subgroups called warps of 32. So, of course, you're allowed to have multiple warps, and these will be executed in turn. So using these groups of 32 cores in the GPU, I'm probably saying things that are wrong here. Peter will correct all of my mistakes, but if there are more than 32 threads, it's not a problem. The runtime, it can do that. It knows there's 8 sets of these things, there's 8 warps, and it will make sure they're all done. But you need to think about vectors of length 32. The same thing with memory loads and stores. When one core in this group wants a bit of memory, it doesn't just load that one number from the memory, from the global memory. Actually, what it does is the loads and stores are done with vector loads and vector stores, like cache lines in the CPU. So it actually loads in 32, well, maybe 16, but it loads in a bunch of memory addresses as a chunk. If you want to so all of this memory access is being done as chunks as well. So again, that's another vector part to this. So you shouldn't think about individual threads. You should really think about groups of 32 threads called warps. This isn't explicit when you write CUDA, but if you want to get good performance in CUDA, you have to be aware of it. And the same is true with OpenACC, because it's the same hardware. So what does this mean if you want to get good performance from a GPU? You need a lot of parallel tasks, loop iterations, elements to your array to keep the GPU busy. Not just 1,000, a couple of thousands, because there's that many cores on the GPU. You need many, many more than that, because the GPU works best when it's swapping things in and out dynamically to hide all of the delays in what it's doing. Your loops, your inner loops must vectorize, meaning that you should be able to do the iterations of the inner loop of your code in parallel. That means that we can write them as vector instructions, so 32 threads in the warp are doing the same thing at the same time. You can have branches. You don't have to use all 32 threads. If you've got an if statement, what happens is that you end up doing the same thing twice, where those that went left, you have a decision. 16 threads went left, 16 threads went right. What does the GPU do? Well, it has to do everything in groups of 32. So first of all, it does the instructions for the left, and those that wanted to go right just sit idle. Then it has to do the instructions for those that went right, and the 16 threads that went left went idle. It's a waste. But it's only a little bit of a waste, and you shouldn't rewrite your code entirely for a one-if statement in your loop. If you've got 100 if statements, all, and somebody's going left, then right, then left, then right, and right, and so on, and you end up with every thread doing something different, that's a big problem. But the odd if statement's not a problem. But you should be conscious of these. These vector loads of memory. You want to do as few memory loads as possible. So what you want is when you load up a bunch of 32 elements from memory, 32 consecutive elements, use them all now. So what that means is that you want coalesced memory access. You want the 32 threads in the warp to load in a block of 32 memory addresses, and each of them process one of them. This is called coalescing in CUDA. What it means in terms of OpenACC, which is very much loop-based and array-based, the fastest moving index on your array should be the one that's being divided up as these vector instructions, the inner loop of your loop nest. There's no internal mechanism for synchronizing between thread blocks. So reduction operations are quite complicated. Of course, they work, but they're more complicated. But also, if you don't write a CUDA barrier inside a CUDA kernel to globally barrier, you don't have an OpenACC barrier like you have an OpenMP barrier. If you need a barrier, you break the parallel region, you break the kernel and start a new kernel when you know it's all finished. Data transfers between CPU and GPU are very expensive. You need the biggest thing, if you've learned nothing else today, just concentrate on data locality. Take the data to the GPU, keep it there, process it on the GPU, only bring back the data you need when you need it. If you keep data moving backwards and forwards, the performance will be awful. And this may mean doing more work than you expected. So GPUs are like racehorses. They can give very good performance, but they're hard to handle. They're not like a cart horse, which is kind of plods along. They're very fast, but you have to make sure that they're very fast in the right direction. Porting an application to a GPU is hard work. It doesn't matter whether this is CUDA or OpenACC. It is hard work. You do need to think about things. Amdahl's law says you need to port a lot of the profile to see a speed up. If you port one routine to the GPU, everything will be slower because of the data transfers, if nothing else. But if you ported 90% of your application to the GPU and the GPU was infinitely fast, you would get a 10 times speed up on your code. If you want to get a bigger speed up, if you want to get a 20 times speed up, you're going to have to port 95% of the application profile. 95% of the runtime should be on the GPU. And that's if the GPU is infinitely fast and data transfers take no time. So if you're going to get good performance, you need to port all of your code, a large portion of your runtime. Now, the good thing is that a large portion of the runtime may not be all of the lines of source because, there's initialization, there's stuff that takes almost no time but has a lot of code associated with it. So you may not be porting every line of your source, but don't kid yourself that porting this routine, in my climate model, is going to speed things up. Climate models have very flat profiles. You're going to have to port a lot of source code to get enough profile on the GPU. A good programming model should help you with that. So that's kind of some of the things I'm going to talk about. And directive-based programming can help you a lot because it means that you spend more time thinking about the port, thinking about where the data should be, when the data should move, and this sort of thing, and less time writing CUDA malloc. And quite often people have found that by doing this exercise of thinking about performance and looking at every part of the code and thinking about things, they suddenly realize, actually, this routine isn't vectorizing on the CPU. I can change this. This is wrong. That's out of date. The sort of housekeeping that you do, the changes that you make to get good performance on the GPU with OpenACC can give you good performance on the CPU because you've improved the vectorization. And modern architectures can do more with that. Should I use OpenACC? Will there be any machines to run it on? Well, of course there are now. What about the future? Well, OpenACC can be targeted at other accelerators. PGI and CAPS already target Intel Xeon Phi or AMD GPUs, other accelerators. OpenACC is more about marking up parallelism in your application than about running on an NVIDIA Kepler GPU. And of course, you're using the same code that could run on the CPU. Will OpenACC survive? You know, it's great now, but you know, in 2 years' time, will Cray say, oh yeah, we're not doing that anymore. So you're going to use something else that's brilliant instead. And you're stuck with legacy code you can't compile. Cray and PGI, I say at least, I mean CAPS, I can't speak for CAPS, but I know Cray and PGI are publicly committed to supporting OpenACC. We have a lot of big customer pressure to continue to support and run OpenACC. A lot of work has been done on Titan, on big applications using OpenACC. If we turn around to Oak Ridge, who pay a lot of our bills, and said, oh, we were thinking we wouldn't do that anymore, they're not going to take, they're going to say, yes, you are. And you know, we're a customer of such size that you don't argue. So there's a lot of customer pressure that we would continue to do that, and of course we will. Will it continue to develop, you know, or will it just, you know, stay like this, but it's out of date? The OpenACC committee grew a lot at the end of last year. CSCS are one of the partners now. We've got a lot more tools and user partners in the OpenACC committee. The new standard is now being finalized. OpenACC is continuing to develop. But will everybody move to use something else? What about an auto-accelerating compiler, one that would just do all the work for me? Please, if you can write one, do so. It would save so much time. But auto-accelerating compilers have never really managed to do proper HPC applications on the CPU. And it's harder on the GPU. So I can't see those making your work out of date. What about OpenMP? They're thinking about accelerator directives. Well, an OpenACC port that you do, the work will not be wasted. It's a very similar programming model. You can transition to OpenMP accelerator directives very easily because you've been thinking about the parallelism, marking up parallelism. Yes, you might need to change the directives slightly, but the OpenMP work is not done yet. It's certainly not a standard. It's certainly not supported by compilers. So my advice would be start now with OpenACC, and you can transition to OpenMP as and when you wish. Cray and PGI are very active in the OpenMP Accelerator Subcommittee. Cray co-chairs it. PGI, Michael Wolff is, says a lot of has a lot of very useful input into this process. He's an expert on this sort of thing. So OpenACC is not going to die. OpenMP is an alternative, but you're probably looking at a couple of years before it's ready. So at first, when you first look at this, it does look to be a lot of material. So, you know, I'm conscious here that we probably have a mix of people. So to try and get an idea, how many people have used GPUs before? A few. And how many people have never used a GPU at all? Okay, good. And the examples that we're going to look at, generally I've got C versions and Fortran versions. It's always useful to try and get a mix. Whose first language is Fortran? And whose first language is C? Okay, so both are there. I hesitate. C++? We'll be treating the subset of C++ called C for these. So the aim of today is by the end of today, if you followed all the material and you would be at the point where you could port a parallel code, a large parallel code, to use OpenACC to run on the GPU. Now, for some of you, that may be far more than you hope to do right now. It's not your immediate priority. So the idea is that if you the material that's in the morning will give you enough to port a simple example. And by simple example, I don't just mean hello world. It's a serial code, one that runs on one core of a CPU or one GPU and does a calculation. It's not a particularly big code, but it gives you the tools to do that. The material after lunch starts to be a bit more advanced. It's looking at how you might do more advanced tuning of your code using OpenACC, how you might port a larger code, what tools are there to help you when the code isn't just a few, 200 lines, you're talking about thousands, hundreds of thousands of lines of code. And when it's a parallel code, what extra features do you need to think about? And then finally, the last lecture is where I'm talking a little bit more about the sort of, the much more advanced features and what's coming in future releases of OpenACC. So I last came to CSCS a year ago to talk about OpenACC. OpenACC was was very young then. Since then, a lot has changed. CSCS has moved to this new building. When I came before, it was out at Mano at the old building, which had donkeys walking around outside. We don't have donkeys here. I haven't seen any, but the setting is, it's not just warehouses. It is a prettier setting. Turdy has moved. The XK6 it's grown as well, and grown from being 2 cabinets to 3 cabinets, and it's gone from XK6 with Fermi GPUs to XK7 with Kepler GPUs. I think it was the first accepted Cray XK7 system, so we're very fond of Turdy. OpenACC has also grown. There's a technical report out saying what's going to come in the next version of OpenACC. That's version 2. That's going to be, in the next few months. In the last year, Cray, PGI, and CAPS have all released sort of full compilers. Get the standard, read the standard, see how you can see what all the facilities are within the language and do it that way. If you want to do that, that's fine. I mean, the standard is, as standards go, fairly short and fairly readable. So, you can download it, you can print it out, it's 30-odd pages, and you can see the whole thing from that. But my approach is more incremental. So if you've got any questions, please do let me know. Jeff just showed the timetable. As he said, this gives us a structure for the day, but we don't have to stick to that. If there's if people are particularly interested in one part or another, then we can spend more time on that. So the slides, as I go along, if you want to look at a PDF of the slides now, the slides and the tar file with the exercises are in a directory under ~A Hart and then Cray OpenACC slides. So if you want to get the material from there now, you should be able to read that directory. If not, please let me know. So hello, everyone. My name is Alistair Hart. Thank you for the opportunity to come here and talk to you today. I work for Cray in their Exascale Research Initiative program in Europe. I'm based in Edinburgh. I joined Cray, I suppose, about 3 years ago, which is really about the timescale, about when we've been thinking about how to program GPUs in a more high-level manner. And this OpenACC programming model has grown out of that. OpenACC is about 15 months old or something. It was launched at Supercomputing in 2011. So before that, I worked in Lattice QCD. I was doing physics. So the way I kind of structured this course is the way I sort of think about these things. And it's more as a sort of user, and how do I do this, how do I do that? So the way I kind of go through the material is sort of developing it almost by examples, and what do I need to know first and what do I need to know next. Now, for some people, some people prefer to kind of just